going to discuss first introduction and what is this law, what is Lamberts law, what are the types of sigma, and what are the types of transition in UV spectroscopy, and I'm going to discuss butadiene transition, butadiene in UV radiation. What is the transition of butadiene? In UV radiation, the transition of electrons in the butadiene transition in under UV radiation. These are the important topics for our examinations also, and also for learning purpose. So, please go through this your textbook, open your textbook, and follow the points what I have taught, what I'm going to teach now. See here, these are the syllabus. So this is actually a textbook M.Sc chemistry in the CBCS so third semester course HCT 301 application of spectroscopy. Application of spectroscopy. Here in the application of spectroscopy, so table of block 3, I am going to take 1 to 8. 1 to 8. Please open your book and see the syllabus. Please observe the syllabus 1 to 8. I am going to take the first unit. Today I am going to take first unit, that is UV spectroscopy. So in the UV spectroscopy, as per our syllabus, so in the UV spectroscopy first unit, it is unit 1, ultraviolet spectroscopy. So objective is Beer's law. So I am just see this Beer's law and Lamberts law. So this is Beer's law and this is Beer-Lamberts law. So and then instrumentation. And these three things are very important for your examination purpose. So this next. So this in introduction, so very important is why some compounds, see this line, why some compounds are colored and others are not. Some compounds are colored and others not colored. Some compounds are and to determine the relationship of conjugation to color, you must make accurate measurement of light. Accurate measurement of light. So the visible, see this one, the visible region of spectrum comprises photon energy of 36 to 72 kilo per mole, and the near ultraviolet region out to 200 nanometer extend this energy range to 143 kilo calories per mole. So ultra radiation having wavelength less than, see this is very important point. So this is very important point. Ultraviolet radiation, see this one, ultraviolet, this ultraviolet having less than 200 nanometer is difficult to handle. this 200 nanometer is there, no? It's less than nanometer, means less than 200 nanometer is difficult to handle, and it is seldom used as a routine tool for structural analysis. The energies noted above are sufficient to promote. So the energies sufficient to promote are exact molecular electron to IR energy orbital. So less than, more than 200 and less than 400 comes under UV spectroscopy. So the energies noted above are sufficient to promote or exact molecular electron to IR energy orbital. Consequently, absorption spectroscopy carried out in this region is sometimes called electronic spectroscopy. It is necessary to correct the absorbance value for this and the other operational factors with a spectra of different compounds are to be compared in a meaningful way. The corrected absorptions value is called molar absorptivity. So next, this definition is very important. So what is Beer's law? What is Beer's and Lambert's law? So according to when a light, if a light passes through one object, this is a light, incident light, this is an object, when a light passes through, object, so when a light passes through a absorbing medium at right angle to the plane of the surface or the medium, this is a medium or the solution, the rate of decrease, so this is definitely decrease, this incident radiation if you consider, the rate of decrease in intensity of the transmitted light decreases. Transmitted light definitely decreases, so some medium, this medium absorbs some radiation, incident radiation, and this outcome means so decreases exponentially. According to Beer's approach, decreases exponentially as the thickness of the medium. This thickness of the medium increases arithmetically. This is Beer's law. According to Lambert's law, can be stated as follows: when a beam of light is allowed to pass through a transmitted medium, see this is beam of light, allowed to pass through transparent medium, the rate of decrease of intensity with the thickness of medium is directly proportional to intensity of light. Mathematically, so proportional to intensity of light. Mathematically, Lambert's law may be expressed as follows. So the decrease minus di by dt, the decrease in intensity with respect to thickness directly proportional to incident radiation. So this minus di by dt, so this is k into I, this is equation 1, where I is intensity, this intensity of incident light, T is thickness of medium, and K is proportionality constant. By integrating the equation 1 and putting I is equal to I naught, so I is I naught when T is equal to thickness at T is equal to 0. So I naught by di by dt means if we cross multiply this, integrate this, I naught by it is equal to kt. After integration, I naught by it means incident light, and this is incident transmitted light, and this is kt. Or it is equal to it. So it is equal to I naught into e to the power of minus kt. This is actually the Beer's law, where I naught is intensity of incident light, it is intensity of transmitted light, K is constant. This depends upon wavelength and absorbing medium used. By changing the above equation from natural log, we get it is equal to I naught e to the power of minus kt, capital K, where capital K is equal to K divided by 2.3. So it is equal to I naught into e to the power of minus 4343 kt. Next, it is equal to I naught 10 to the power of minus kt. Beer's law may be stated as follows. So according to Beer's law, intensity of incident light decreases exponentially as the concentration of absorbing medium increases arithmetically. So intensity of incident light. See the intensity of incident light. See this is the example. The intensity of incident light decreases exponentially as the concentration. So if we put same concentration of sample here, 1 mole, 2 mole, 3 mole, if the compound here, the above sentence is according to intensity of incident light. See this one, intensity of incident light decreases exponentially as the concentration of observing medium increases arithmetically. The above sentence is very similar to Lambert's law, so where K and K dash, small letter K dash and big letter K dash proportionality constants. C is equal to concentration. By combining equation 3 and 4, we get 3 and 4 we get, if we combine the equation, so where this C is equal to concentration by combining this above equation, where epsilon r is absorptivity, this is called epsilon r, absorptivity, a constant depend upon the lambda, incident wavelength of the, where lambda is nothing but wavelength of the incident radiation and nature of observing material. The value of epsilon r will depend upon the method of expression of concentration. The ratio I0 by T is termed as transmittance T, and the ratio log I0 by IT is termed as absorbance A. Formerly, absorbance was termed as optical density D and the exhibition coefficient E. The ratio I0 by IT is termed as opacity, thus A is equal to log I0 by IT. So from the equation 5 and 6, A is equal to epsilon r BC. From combining all the equation, so finally A is equal to log I0 by IT, that's equal to log 1 by T. So log 1 by T means a transmittance. See, this is transmittance. So if we change this logarithm to upper 1 minus log T, then ABC is equal to epsilon r BC. So instrumentation is available in the textbook. Let's go through this. Theory is no need to explanation here. Let's go through the SLM. Then, if time permits, I will discuss in the later class. When we refer to molecule as being excited to a higher electronic